Good morning, YouTube. It is Coffee Talk with Haze, episode 17. And today I would like to continue the past two talks that we've had about ground and powering your synthesizers, essentially talking about voltage. Today I want to talk mostly about current. So there's going to be some overlap between voltage and current, and I might actually dispel a few kind of myths or maybe uncloud a few hazy areas that you have about this subject. We'll see. As usual, I'm not prepared for this. It's just stream of thought. We'll see how it goes. So I first want to start off by kind of reiterating some of the principles that we've already established. More coffee first. So, audio is not sound. Very important to understand that. Audio is not sound. The second thing is that pretty much every electrical device that you're using is using amplification. You may not realize it, but probably not just once, but multiple times. You may have heard of something called a buffer. You may have heard of these things called buffered mults. Well, when you hear buffer, that's a usage of an amplifier. So that's another amplifier. So anytime you run across these amplifiers, your signal is going to get essentially copied. Now maybe some of the original signal gets leaked back into there somehow, but for the most part it's better just to think of that the current flow of your input signal, when it hits an amplifier, it terminates. When it hits the input of that amplifier, it effectively terminates. And what comes out of the amplifier is a replica of that input signal, but usually at a larger power, either in voltage or current. We'll get to that hopefully in a little bit. Using the actual, what's called the power rails, the most, well, in this particular case, we'll just say 9 volts or 12 volts, whatever your input voltage is, and ground. I don't want to get, again, I'm trying to avoid being technical with this stuff. This is going to probably be more technical than not, unfortunately. If you are not a technical person, I'll try not to blow past you very fast that you're like hanging on to the tailpipe of the car as we're just dragging you along. That is no fun. That is no fun at all. So then the big thing becomes, what is the difference between voltage and current? Now you can go right now anywhere. You can go out on the street and just ask somebody, hey, what's the difference between voltage and current? And they can probably give you a fairly accurate answer, even if it's not exactly precise. But what I'm talking about is, okay, why do we use voltage? Why do we use current? Because a lot of times, almost every application, whatever the application is, we're focused on one or the other. It's almost like quantum physics. Is it a particle or is it a wave? Is it voltage or is it current? Well, it's not like quantum physics in that regard, but in terms of our application, we're just kind of focused on one thing, current or voltage. So I like to think of voltage as communication. I know that's radical. A lot of people are going, whoa, what the heck are you talking about? But when you look at all the applications of where we're using voltage, apart from powering the devices itself, apart from biasing inputs to amplifiers itself, those are the actual sort of utilitarian versions of this. And with all of that comes current concerns as well. But when we're actually making use of this stuff, sending men to the moon and women to the moon, sending caterpillars to the moon. That's my new quest. I'm on a quest to send caterpillars to the moon because that is just randomly odd thing to say. And I love doing that. Is that, sorry, that was a good one. I derailed myself on that. Is that with voltage, we can use voltage to communicate. 2 ways, just to give you 2 examples. One, digital communications. Square waves, pulses. Determining like how many we send gets translated into a binary code. And that gets picked up and turned into some meaningful thing that a human can understand. It's one form of communication. But also in terms of sending well, I don't want to get into radio waves just yet because I haven't done enough studying to really know the fundamentals of that kind of stuff, because that's a little bit over my head. Ooh, that's a good pun. But seriously, in terms of amplification itself with headroom, I like to think of that as communication as well. That's a huge stretch. But what we're doing with that kind of amplification, with voltage amplification, with headroom itself, is we are allowing a signal to get bigger without clipping it. So in other words, if I've only got 6 volts to work with, well, that's it. That's the maximum output that I could ever hope to have. But with 12 volts, well, I've got twice as much to deal with. Now think about it in terms of resolution. You've got all this resolution to deal with. With 24, you've got even more. It's even better. But I'm getting off the beaten path right now. I do apologize for that. I really want to stay focused on current. But again, it's almost impossible to go back and forth. So what is current? What is current used for? Well, current, I like to think of is something that we can use as a realization. So if voltage is communication, then current is realization. It takes us into the real world. Not the circuitry isn't the real world, but it's not our world. So current takes things into humans' world and, the world around us. What we can see, what we can touch, what we can pick up. That's a better way of looking at it. I don't know about you, but I can't pick up a single atom, let alone a single molecule or electron. I should have said that in another order, but you see what I'm trying to say. So, take the speaker for example. It takes voltage to, turn it on, but with that voltage to power it also comes current. So again, this is one of those things where that's a utilitarian example where everything that we're dealing with requires, that's just a basic fundamental requirement. So let's move past that for the moment and just think about the application. There is a magnetic mechanism in here like that is moving back and forth, and the change in voltage causes that to move back and forth, but more importantly, it's the change in current. So yeah, it is the change in voltage, but if there isn't enough current to actually do anything, it's not going to push this very much. It's not going to be very loud. So we need more current to actually push the load. I hope that makes sense. I could keep reiterating that over and over and over again, but I'm basically just going to keep saying the same thing in different forms until I eventually say the wrong thing. So that's why I like to think of it as a realization application. And there's all kinds of other things here. I'm not really sure about light bulbs, how much voltage versus current it takes to get a light bulb to shine. And I'm talking about the old incandescent light bulbs at this point, not the new LEDs. That's a different concern. It's nothing terribly complicated, but I want to keep things, real simple here. So one of the things that I like to do when I think about this stuff is that I think about like a quad grid, or just like one section of a grid. And across this axis is current, the x-axis is current, and the y-axis would be voltage. So usually when you see something that we're using with voltage, it's never just a thin, straight line drawn with just a simple pencil. In other words, like the current won't just be like, it will be, but you think of it more as kind of like, okay, yeah, we got some voltage, but we've got some current, and the current, we may be using this much, maybe using this much, maybe just using a line. But you see what I'm saying? This part becomes variable, and then likewise, it kind of morphs like this. So now we've got different voltage and different current, and this kind of does it this way. I'm looking for a good example where we're dealing with a perfect square, the exact amount of voltage and the exact amount of current. And I don't know that anything out there really does that. It's usually like a whole bunch of voltage, or it's a whole bunch of current, because that's the relationship, and they're tied together through something called resistance. And this is what Ohm's law basically is that it shows the inverse relationship between voltage and current across resistance. And that is so simple, but it takes a lifetime to really wrap your head around, I believe, because there are so many little subtle turns with this kind of stuff. And it really, okay, I know that my brain has been twisted and battered back and forth over the past 2-3 years learning this stuff, trying to wrap my head around it. And right now I feel pretty confident. I'm feeling a lot better about things, and I'm definitely I'm not stopping with my studies on this stuff. Okay, so it's really easy to measure voltage. And the other thing that's kind of interesting is that, okay, well, think about it yourself, right? You always see voltage on a lot of this stuff, especially on the back of devices. You'll see the voltage. You won't see the current requirements. You will see a current specification on the back of a wall wart. And so for example, the electroharmonics pedals that I mentioned in the last talk were rated at 200 milliamps. And I mentioned that, well, that's not a whole lot. And it really isn't. It's enough for a guitar pedal. Guitar pedals tend to run maybe 80, 90 milliamps. Maybe some of the other ones run up a little bit higher. But they got pretty low voltage requirements. And it's pretty, they're fairly low power requirement devices. But even our kind of getting into our beefier synthesizers, even one that has, a direct 120 volt connection in, where the transformer is on board and all of the rectification of AC to DC happens within the synthesizer, those, you don't even really see a current requirements for those either. I'm not exactly sure how much they would run. I want to guess, honestly, even those don't run a whole lot. They may get upwards to 300 milliamps, maybe even 400, maybe half an amp, maybe an amp. I wouldn't think any more than that, though. I would probably theorize that the older synthesizers take up more power than the newer ones, most definitely. So that is one of my strikes against wanting to own a lot of old vintage synthesizers. And again, though, I need to actually do the actual research before I make a conclusion based on that. But I'm pretty sure they take up more power, and they we've learned a lot of things since then. That's the beauty of all of this. As Josh from JH Pedals says it, these companies, they want to make things better. They don't want to make things worse. I mean, yes, there is a thing called planned obsolescence, but that applies more to appliances, your dishwashers and your washing machines and your lawnmowers and that kind of stuff. And hey, nobody talks about those companies very much, right? What's the business practices of those companies and their planned obsolescence? And so the last I looked, with synthesizers, they last a long time, and they seem to be a lot more repairable than all these other devices that I see on the side of the road all the time, broken down, that nobody wants to bother repairing because it's not worth it. So, what are your considerations for a wall wart, supplying enough current, how do you say it? Well, yeah, you can say it that way, to your devices. Okay, so I didn't mention this in the last talk. If a wall wart is rated at 200 milliamps, that means that's all it can provide, is up to 200 milliamps. So you probably don't want to go powering a lot of your synthesizers with the electroharmonics pedals that are only rated at 200 milliamps that are really supposed to be used for guitar pedals. Now, last time I mentioned that I believe the reason why those pedals were so big and they had low current supplying capabilities was because of the quality involved, and they were more concerned with, I hate to say it, but there may be another thing, and that's just simply that Electroharmonics doesn't want you to just buy one of their wall warts and be able to buy a 1-spot 5 guitar pedal splitter and power up 5 of their pedals with one wall wart, which you can totally do. Because there are wall warts that are rated for up to 2-3 amps. I've got one over here that's rated for 3 amps. And yeah, it could totally daisy chain a whole lot of stuff on it. The problem with doing that is that everything has to be either center positive or center negative. You could build your own individual adapters. It gets a little crazy there at that point, though. I don't like to mix and match positive and negative stuff on one cable like that. It's a little kind of weird. There are a few boutique pedals out there that may not like having reverse voltage into them as well, so that's another consideration. But so in terms of the voltage on the specification on the back of the wall wart, like I said before, you don't want to use anything over. Well, you may be asked this question, like I mentioned in the last one, that Electroharmonics wall wart, which, by the way, a couple times I said pedal at the very end of that video, and I meant to say wall wart, not pedal. I hope you didn't get confused by that. But that Electroharmonics wall wart was rated at 9.6 volts, I believe. So what's up with that extra 0.6? It's okay. It's not really going to, I'm going to show a few things here in a second, and it's okay. A little bit over 9, if it's rated at 9, it's probably just fine. The thing is that if there is a voltage regulator on there, let's say like there was a 9-volt voltage regulator, then you really do want to hit it. You do want to power that device with a little bit more than 9 volts to make sure that you get over the voltage requirement for that voltage regulator. But man, did I just get super technical there. I do apologize. But what I'm trying to ease your concerns about is if you see that's like, oh, this is 9.6 and my device is 9, is this going to be bad for it? No, probably not. I don't see how. One thing I do want to touch on is that the business card sequencer that I showed you was rated from 7 to 15 volts. Okay, what's up with that, you may be asking. I've also got some guitar pedals that take anywhere from 9 to 18 volts. What's up with that? Well, first of all, we got to back up. Is it a digital circuit or is it an analog circuit? These guitar pedals that I'm talking about are analog. So a lot of this analog stuff can handle 9 to 18 volts, no problem. No problem at all. The issue, of course, is making sure that you don't blow out an LED, because those can be like very tightly. Those require resistors. LEDs require resistors to prevent from just being burnt out. I don't want to get into those details, but that's the easiest way to protect a resistor. There's other ways, but the cheapest, easiest way is just to use a resistor that's properly rated. Now, you can get right on the verge of that rating, right? And if that's the case, and you went from 9 to 18 volts, then yeah, you're probably going to blow that LED. But no pedal builder in the right mind is going to do that, I don't think. But that's just something I want to talk about because yeah, that is a concern. But for the most part, that's pretty much it. Any of the transistors and the operational amplifiers inside, they can handle 9 to 18 volts, no problem. It's just the LEDs. Now, digital circuits, as I said before, can only handle 5 volts. So that little business card sequencer was a digital circuit, and it had a 5-volt voltage regulator on it. So again, here what they're asking is give me more than 5 volts. In this case, give me 7. Probably get by with 6. But you see, they don't want to put 6 because it might not work. Somebody's calling them up saying, "What?" See, a lot of times what these manufacturers are doing is they're calling they're doing what is called CYA, cover your butt. And it works because flooding their call center with calls is not bumping up their revenue at all. Okay, so where do we go from here? So that's pretty much the concern, though, with trying to understand the specification on the back of a wall wart for amps, is that what you're seeing, it's like if you have a wall wart that's rated for 2 amps, and your device only needs 200 milliamps, totally okay, totally okay. Devices draw current, so they draw what is needed. So the more that is provided, the better. You might say, okay, so why aren't all of my wall warts rated at 3 amps? And probably safety is what I would guess. Probably safety. One, you probably don't need that much. If you do start using that much, you have a few concerns. I've actually destroyed one of my wall warts pushing it too hard with one of my own power devices that I built that I use to power my 6 Roland boutiques. And yeah, that happened. So I'm not really sure what I did wrong there, but lesson learned at the end of the day, it's that, yeah, the more power, the more responsibility. Food for thought. Okay, so moving on, how do we measure how much current my device is drawing? Well, that's not very easy. Usually, let me back up a little bit. It's real super simple to measure voltage with the multimeter, which I don't have here with me. But you can just imagine I've got my 2 leads here, my multimeter, and you have, you touch the ground to ground, and wherever you want to measure like a certain voltage point, touch it, and your multimeter will show you the difference in potential between voltage on those 2 points. If you get the meters reversed, it will just show you a negative sign instead of a positive sign, or vice versa. Oh, I would love to get into negative voltage, but now is not the time, I don't think. I will say this, though, because we're talking about current. Negative voltage just means the current Negative voltage just means that the current is going in the other direction. If it's going in this direction, positive, the negative, it's going in the other direction. That's it. And that's why it's alternating current, because it's going back and forth, like a sine wave, in the case of the power coming into our residence. In the case of the audio signal being picked up by a microphone or a guitar pickup coil, it's going to be a wild looking, kind of randomish signal. If we're putting in a known waveform into there, we're going to hopefully see that waveform with a bit of distortion, because we're picking it up with a microphone or a coil, and there's going to be some error that's going to be picked up inevitably. Okay, so the way to measure how much current that your device is drawing is you have to break the circuit. Well, there's 2 ways. Well, 3 ways really. Okay, 7 ways. No, just kidding. 3 ways I'm going to talk about. The first way is to break the circuit. And what that means is that somewhere in the circuit, if I have to, I've got to literally snip a wire or scratch out a trace, and then I can take my probes and then figure out how much current is drawing through there. That doesn't sound fun, does it? Yeah, it's not. It's kind of like surgery all of a sudden. Another way is to use one of those multimeters that has the clamps. But again, if you're trying to do this on a PCB, good luck getting that clamp around a circuit trace. Also, you may have to cut into a cable to get just to the hot conductor, the hot conductor inside that cable, which may or may not be shielded, by the way. And the last time I mentioned a cable and I said it was shielded, that particular one wasn't shielded. It was just insulated, further insulated with another protective coating or rubber sheath, whatever you want to call it. But get one of those multimeter with the clamps, and then the clamp around the appropriate conductor, and then the magnetism that's picked up will tell you how much current is being drawn. It's pretty freaking wild, isn't it? Okay. Then a third way that I'm going to talk about is to get a device like this little Drock USB tester. This one is only good for 5 volts because it's a USB tester. Let's see. Yeah, this one's, I think it handles up to 3 amps. And right now we see that the battery pack that I'm pulling from is supplying 5.3, 0.2 volts to it. Hopefully you can see this well enough in the camera. And I already tested running the camera that I'm using right now through this. And in resting state, when it was just turned on and not recording or playing anything, it was pulling 200 milliamps. That's very, very interesting, isn't it? 5 volts and it's pulling 200 milliamps. So when we think about Ohm's law and you think about the inverse proportionality of voltage and current, it starts to make sense though. With the same amount of resistance, the less voltage, the more current. Isn't that crazy? And so that is what gets interesting when we're dealing with digital circuits, is that they tend to use a lot of current. And we don't need a whole lot of current when we're doing that stuff, so all of that gets transferred into heat, and that's why we deal with a lot of heat issues in computer engineering, those kinds of digital circuits. Not our devices so much. It's not so bad here. But when I hit record on the camera, it jumped up to a little bit over 300 milliamps. So I'm just kind of giving you an idea, right? So, okay, so yeah, right off the bat, it's pulling enough power to be really more than that electroharmonics pedal was rated for. Again, it's a different story because that's a 9-volt pedal. This is a 5-volt tester, and the camera is a 5-volt device. And, well, darn, I was forgetting what I'm saying. Let me drink some coffee. All right, and then as soon as I started recording, however, pulling even more, like another 100 milliamps. So I'm trying to get you to think a little bit about that. Because there's a number of people out there in our community and in hardware jammers who use battery powered stuff. So this is where I'm going with this. So what I'm going to do now is hopefully not make a whole bunch of noise on the table, but you can see I've got my super cool Kai Professional, what is this, the MPX-8. And this is one of those controversial samplers, but I'm telling you, man, if you could pick one of these up for 50 bucks, why would you not have one of these? For $50? I mean, hey, look, if it breaks on you, it's not my fault, but I'm just saying, this is a cheap sample player. So what I'm going to do is I'm going to power it up. I'm going to keep it in my lap, so hopefully that won't make a bunch of noise. Okay, so we are powering up. And let me get this so we can see it. Okay, so we've gone down to 4.91, whatever. Now we're back up to 5 volts. But as you can see, we're drawing 240 milliamps. That's the blue number. 0.24 amps, or 240 milliamps. So what I'm going to do is I'm making sure that everything's loud enough here. And I'm going to turn on my speaker so we can hear this too, because I want to make sure which sample that I play is the one that I want to play.
This is for the cops.
Yeah. So if we can watch very carefully, I want you to watch the amp number. And it should go up.
This is for the cops.
Yeah, it went up, 20 milliamps. It did that when it was driving sound to its output. The amps jumped up just a little bit.
This is for the cops.
Now, if I turn this down, pardon me for being so loud, so we don't hear it anymore, it doesn't shoot up to 0.26 like it used to. You see what I'm getting at? It's as I'm driving audio signal to the output, the more that I'm driving, the more amps that I'm pulling. I hope that makes sense. And
this is for the cops.
I think you can hear that. I don't know. But at any rate, yeah, this is for the cops. That's from Fletch, by the way, one of my favorite movies. It's a silly movie. Super silly. There's just a lot of cool scenes and a lot of great quotes you can pull from it. So, let me turn this off real quick and turn on my speaker. It's my theory then that if you are a battery-powered hardware jammer, right? If you get a bunch of Korg Volcas and you want to battery power them and play them outside somewhere or wherever, you might want to think a little bit differently about your gain staging. So your typical strategy for gain staging is that, like for this device, it's the output. I want to drive this up. It's on a scale from 1 to 10, the main volume. I want to take it up to 10 when I'm recording with this. And anytime I'm recording, I take it up to 10 because that way I'm getting the most volume. I can control the individual volumes of the samples as well. The samples themselves are going to be at differing amplitudes as well. All of this matters. The idea is to not get distortion. So if I'm not getting distortion, I want it to be as loud as possible. And that is your usual strategy for gain staging. I think you should change that up a little bit if you're going to do things powered off of batteries, because you might be able to get just a little bit more life out of your batteries if you turn the main volume on these devices down a little bit. You're going to introduce a little bit more noise inevitably. The more you turn it down, the more noise is going to be introduced. There's a balance point though. So if I'm running this at 10, and if I'm performing somewhere live and this is running off of a battery, I might want to try to pull it down to 6 or 7 and just see how that works out. But again, let's think about it like this. It was running at 240 idle. When I was hitting a hard sample, it was going up, to 260. If it was jumping up to like the camera, for example, from 200 to 300, yeah, that's a major consideration. But again, this particular device may be pretty light. Some other ones may actually have that kind of difference in driving the output at different levels. Experimentation is what you need. Now, the question is where can we find one of these for like 9 volts and 12 volts? I haven't really looked into it yet. I don't know that they exist. It'd be nice if they did. Maybe I could build one myself. These little digital readouts are, they're not, they're not as hard to put together as you might think, but they're not as easy either. What I would definitely do is I would try to leverage some kind of pre-built sensor kind of thing and just add that to a device myself and configure it so that it runs at a certain voltage range like 9 or 12. That would be my guess. I do know that these little displays exist, these digital displays exist, because I use them on my power my power bench supply that I built. It was a Jameco kit that I put together myself, and I added my own digital displays so I could see how much voltage is being pumped out of those suckers. Okay, I think this wraps it up. We're pretty good to go. I do want to say I pulled this mixer out and I don't remember why I was going to talk about it. I guess it was, yeah, because I wanted to, okay, I know why, because I wanted to talk about the current draw theoretically for something like this. Because here we have a mixer, right, and we're using this to increase our volume, mix the things together, and well, this is really mostly preamp material. It's not a power amp. So what's coming out of the output of here is loud enough to be picked up by something that can then turn it into a power amp situation. And furthermore, it only runs off of 9 volts. So yeah, but by the way, these are some of my favorite mixers. I love these things to death. I think their biggest critique was that the DC jack is non-standard. You can't fit a standard 9 volt center negative. I can't remember what the millimeter size is. Was it like 3.55 or is that the, I can't remember. I think it's 3.55, whatever, 2.55 DC connector into this. But look, it's center negative. It's center negative because so many guitar pedals are center negative, and all the wall warts with those for those associated guitar pedals are center negative as well. But what I did is I went to Tata.com and I bought some PCB mounted DC jacks that I've had around forever, and they are the right size for all of your standard wall warts, and I replaced this sucker. It is the easiest modification I think anybody can make. And you may be saying to yourself, well, why don't you make a video? Because I got this one and I got another mixer, and guess what? I did make a video on showing how to modify these and put in a new DC jack so that you can use any wall wart center negative 9 volt for it. And in the process of filming that video, when I was actually doing all the real work on the circuit, I forgot to hit, I hit record, but the camera was not recording. How many times has that happened to us, right? Okay, well, YouTube, we'll see you next time. Hope this made a lot of sense. If it didn't, too bad. See you. If you look very carefully at the bottom portion of the moon, you'll see the shadow that is formed by the Earth. And that shadow forms another sort of circle around the circumference of the moon. That, folks, is what we call a sphere. And if that sucker up there is a sphere, then guess what we are on? Another sphere.